All right, so the equation that actually creates the curve, if we were to type it into our calculator to make those beautiful bell-shaped curves, is the given following function that we have, which I'm just going to write here. You do not need to know, and you will never use, because it's a built-in function into the technologies that we use. But I include it here because it is a pretty beautiful equation in the sense, okay, that it has, these two symbols in it are mu and sigma from earlier, mean and standard deviation. So the curve, its shape and size does depend on the mean and standard deviation. But it also has these kind of two crazy numbers that we learned back in algebra, the two irrational numbers, pi and e. Okay, it has, an exponent, it has a square root, it just brings lots of pieces of mathematics all together in one function. And interestingly enough, many things in our world are described by this crazy looking equation. So just as in a discrete probability distribution, the object is to find the probability of some event occurring. However, unlike in a discrete probability distribution where the event can be a single value, in a continuous probability distribution, the event must be a range of values. And again, that comes back to the concept that for continuous random variables, probabilities are going to correspond to area under a curve, and there is no area under a curve at a single point. Okay, so we always need to have a range of values on the x-axis. All right, so now we're interested in finding the probability of the random variable x occurring in some range between a and b. Again, this probability statement given here, okay, the probability of getting an x between and inclusive of a and b is the same as the probability of getting an x strictly between a and b. This is only true for continuous random variables. So again, we need to be careful when we go back to chapter 5 where we dealt with discrete distributions. This is not a true statement. Okay, the first probability, the one where we include the two endpoints, more than likely is going to be larger than the probability where those two endpoints are not included. Okay. All right, so the probability that x is between inclusives of a and b is the same as the probability of x strictly between a and b, because both of these are just the area under the curve above that interval. And again, throwing in the endpoints doesn't add any more area under the curve. Okay, so again, this quantity is this area in here. So before looking at the process for finding the probabilities under the normal curve, we're going to look at something called the empirical rule that does give us some approximate values for these areas, for common ones that we look at when we start looking at inferential procedures. So the empirical rule is just an approximation, and it will only be used in this section to give you an idea of what the size of the probabilities is for different shadings. A more precise method for finding these will be demonstrated in the next section. So please do not use the empirical rule unless you are asked to use it to make rough estimates. So the empirical rule tells us that for any normal distribution, approximately 68% of the data will fall within one standard deviation, and approximately 95% of the data will fall within two standard deviations, and approximately 99.7% of the data is within 3 standard deviations.